So it's great to be here, and I'd like to welcome my panel members to the stage. First of all, Professor Huai, who is president of Beihang University, I met many years ago, who is an expert on software and middleware research, especially trustworthy computing services and so on, and information security. Professor Huai. My next panelist is Professor Choi from KAIST, who is currently head of computer science department, who is an expert on natural language processing and knowledge mining, and has been looking at semantic web technologies and information synchronization in Wikipedia, as well as ontology-supported data management. Professor Choi. My third panelist is Dr. Jimmy Liu from A-Star in Singapore. He works for the Institute of Infocom Research on medical imaging. So Professor Chu is heading the feature and segmentation group and intelligent medical imaging in this institute, and has been working on MRI, CT, and retina medical image processing with the Singapore National Eye Institute. Jimmy Liu. And my last panel member is Professor Tsuji from Department of Computer Science in the University of Tokyo, who is also an expert on natural language and speech. For my purposes, I set up a centre in the UK called the National Centre for Text Mining in Manchester, and Professor Tsuji is the scientific director there and Professor of Text Mining in the School of Computer Science in the University of Manchester. Professor Tsuji. So what I'd like to do is then begin briefly by outlining some of the ideas of the fourth paradigm. This is the fourth paradigm book, which I'll talk about in a moment. And it's concerned with this tidal wave of scientific data, and you can see in almost every research journal that we're being absolutely bombarded by data. We'll collect more scientific data in the next 5 years than we've collected in the whole of human history. It's really becoming a challenge for scientists of all varieties to know how to manage the data. Just to give you two examples, we're all familiar with gene sequencing, and only a few years ago it cost billions of dollars to sequence a single genome. We're now down to $10,000 or something like that, and in a very few years, less than 5 years, it'll be down to $100 or less for doing everybody's genome. And that will really change the way we do medicine. It'll change the way we design drugs, and have huge consequences for many industries. And just to take another example from science, astronomy and particle physics, this is from The Economist article. In the year 2000, the Sloan Digital Sky Survey, of which you probably saw some images in Curtis Wong's talk, collected more data in its first week of operation, surveying the sky, than has been collected in the whole of the entire history of astronomy. So things are really changing, and in 2016, a new telescope in Chile, the Large Synoptic Survey Telescope, will acquire 140 terabytes in 5 days. Every 5 days it'll survey the entire night sky, and that's more than the Sloan acquired in 10 years. And of course the particle physicists have traditionally been at the extreme end, and the Large Hadron Collider at CERN generates huge amounts of data in each collision. You filter it, but each experiment will generate petabytes of data per year, and that really is a problem for the scientists to organize and manage. So a digital deluge in research, sensor networks, satellites, high throughput lab instruments, supercomputers generate huge amounts of simulation data. How do we analyze that? How do we visualize it? How do you do data mining, workflows, searching, and so on? These are challenges that the computer science community has an opportunity to work with the scientific community. And finally, when you spent a lot of money getting this data, you will in the end need to keep some of it, and how to curate that, how to store it, how to archive it, so you can still read it in 5 or 10 years from now. And so this is, and reuse and interoperate with other data sets. So these are the challenges, and there are real challenges for computer science in terms of provenance and curation and automatic semantic markup and so on. So our colleague Jim Gray, who alas is no longer with us, called this new phase of science, which is data intensive, a fourth paradigm, by which he meant that we've been taking measurements of the natural world for thousands of years, since the Greeks and the Egyptians and so on, and trying to measure the world around us. And since Isaac Newton and Galileo and so on, we've formulated laws of nature as mathematical equations. And so that was the onset, the beginning of theoretical science. And there are these two ways of exploring the scientific world: taking data and exploring and analyzing the theoretical equations from which you could then predict more effects and take more data. But in the last 50 years, as we all know, the computer industry has been with us. And Ken Wilson, who was a Nobel Prize winner in physics, I used to do particle physics, he got his Nobel Prize for the normalization group, but he was very enamored of the fact that you could use computers to simulate conditions that you can't reproduce experimentally, and the equations are too complicated to analyze analytically. So he felt that there was what he called a third paradigm for the way of doing science. So you have experiment and theory, but there's a third paradigm. You can explore science like galaxy formation, like climate modeling. There's no other way to do this other than to do simulation. And that was the third paradigm. Jim saw that actually we were now approaching a fourth paradigm. To do computational science, you need to know about numerical algorithms, you need to know about computer architectures, parallel programming languages, and so on. And that's a set of skills that scientists and computer scientists need to have. But to do data-intensive science, you need a different set of skills. You need to know about managing data, databases, data mining, data visualization, which are very different skills than actually has been required of scientists up to now. And so one of the topics we're going to talk about is how we create those type of scientists with those skills. And I used to work on eScience, which is, if you like, the set of tools and technologies from computer science that can help the scientists do this new type of data-intensive science. So I think there's a real opportunity for computer science to help the scientists solve some of the problems facing humanity in terms of health and environment. So just to give you a couple of examples in a moment, Jim Gray therefore saw that each field X could be chemistry, so you could have computational chemistry, but now you were having chemoinformatics. You could have computational biology and now bioinformatics. And I went to a meeting a few weeks ago at Caltech where they were talking about astroinformatics. And we had a talk last week at our eScience conference in Berkeley on archaeoinformatics, about the informatics of archaeology. So these are the sort of skills you need to have. This is a slide from Jim Gray, you know, the genetic problems of data ingest, taking huge amounts of data in, a common schema, how to organize it, how to reorganize it, how to query it, and so on. New skills that scientists need to learn. So two examples, bioinformatics. David Heckerman here, who was used machine learning techniques to introduce to Microsoft the first spam blocker, is using similar machine learning techniques to attack lots of problems in biology, which are data intensive, finding subtle signals in large amounts of data. So he's working with a medical community in Harvard, in Oxford, and in Africa to try and actually find a vaccine for HIV. And we have actually some promising progress, and we're actually producing a trial vaccine now. And that's how computer science, in the form of machine learning in this case, can actually help the medics solve some problems in their domain. And we hope that that's successful. Another example is also dear to my heart. I live in Seattle, and it's a very high earthquake zone. And here they're instrumenting the seabed where the Pacific plate goes under the Northwest America plate, and putting sensor data there, so we'll get data streaming in 24 hours a day, 7 days a week, 52 weeks a year. And the field of ocean science has gone from being very little data to suddenly being flooded with data overnight. And we're experimenting with how you analyze that. Do you use the cloud? How do you store it? And so on. So many interesting, exciting applications. So this is what this contains. It contains a collection of essays by scientists and computer scientists looking into the future to see where their field is going. So there's a section on Earth and the environment, health and well-being, research infrastructure, and then a fourth area, which is about the revolution that's taking place in scholarly publication. Linking text to data is important for reproducible science. It's an astonishing fact that in astronomy even, the astronomy papers, if you want to go and reproduce and do the analysis again, you can only find the data in about 10% of the cases. So actually getting hold of the data on which the research was done is increasingly difficult. Getting hold of it to combine it with new data, to do new analysis, is what we need to enable, and that's going to change the way that publishing evolves. So this book is available. It's under a Creative Commons license, and so you can download it for free, or you can get a version on Amazon for the Kindle or print on demand. And we've just announced last week that we're making with Nature Networks, we're doing, if you like, an electronic version of that, where we're getting a new collection of essays from other scientists from all over the world, and hoping at one point maybe to produce a second volume. Well, I think that's enough introduction. So what I'd like to do is now turn to our panel. These are the sort of general questions that we gave the panel. Potentially important technologies, semantic technologies, what about the cloud, and how do we educate the students? And I'd like to ask Professor Huai to give us a short presentation on his ideas. Professor Huai.
So thank you, Tony. So good afternoon, everyone. So just after Tony's, so I hope to give my opinion about what's the challenge or potential technique for scientific data error. So I think, so just as mentioned by Tony, so we have to face to a tidal wave of scientific data. So what's the big challenges for internet software in this era? So in addition to scientific data, so we also face many problems because various crises facing humanity. So we know there are lots of things related to data. And also in this year, economists published a special issue about data deluge. So how to deal with data so that we can discover the new rule, new science, and also give us a better way for society. And how to provide a platform to deal with this data. So what's the big challenge for software? Maybe there is some different from software engineering or traditional software developing. So in one hand, we know all of the data should be dealt with storage or computing. But we also know, in the other hand, so there is a big gap between global information created and available storage or computing power we have for actual data. So how to deal with that? Because we know the energy consuming in IT domain has become the number 5 in the world. So how to provide a way to share resource so that we can efficiently utilize the resource and provide resource sharing to deal with data. So I think the first challenge about this resource sharing is the science or foundation for that. Compared to operating system, we know process-based algebra, we have time-sharing traditional operating system. So it provides a way for resource sharing in mainframe or PC computing. But for network, what's the way for resource sharing? Maybe the common way is to provide virtual machine, to provide a virtual machine network or virtual computing environment to share resource. But what's the basic foundation for the resource sharing? So how to provide the time and the space domain sharing resource? That's much different from traditional operating system. So how to ensure its high availability in case of the environment or cloud computing failure or conflict? Finally, I think maybe different from software engineering traditionally. So what's the new paradigm for software rapid developing tools? So maybe we can compare it to the card manufacturing. So maybe we can find some way for application or for some sector. We have a way to organize some service into application so that we easy way or rapid way to develop a new application. So what's the new paradigm? Suppose we have many service and software. So how to establish the new developing tools or method to have the application to own their own application? So develop new software for various data process requirements based on the number of service or components, or we should find a way for application. So in this area, we also do some work in IWIC platform to organize the resource and the sharing. So because of the time limitation, I just gave the show about that. And also based on that, we have from the Crown into develop a Crown system into IWIC platform. We hope to provide a model for cloud computing or just a virtual computing environment. That's all. Thank you.
Thank you very much, and Professor Choi. Thank you.
One of the major achievements of semantic web technology in this stage, I think it is LOD, linked open data. That is the result of web data integration based on pivotal data web called DBpedia. So in the right-hand side picture, you can see all of the link between many kind of data web. So, but it is a syntactic link. So the current stage of research is going to make a semantic data web. That means that we want to give some semantics for every link between a data web. And I think after that, we can go to the semantic web, because the semantic web must have some functionality of reasoning based on logics. And now in this stage, semantic applications in this domain, in this area, has been adapted to some domain. And also a huge information knowledge of e-government now is launching slowly by some government. But still, semantics does not touch the actual users. So for most of the web users, semantic web is not yet a reality. So open source semantic application is very, very rare, and there is a high barrier to develop and use the semantic applications. So we have challenges about why semantic web still is not in there. I think there are 4 problems. So first one is low user adaptability. That means that problem is in how can we adapt existing RDF data to the specific user's purpose. RDF means that in the right-hand side, it is an information box in Wikipedia about the Busan city in Korea. So here in the table of column, in the left side is metadata, and the right side is value. So it is a triplet. So that is converted to RDF data. But there are many inconsistent metadata terms. So every user cannot meet with this consistent metadata. For example, it is a small example. So users, I think the user-created ontology must be meet with the already made huge size of ontology. It's like an ontology cloud. And second problem is multilingual imbalance. For example, in Wikipedia, there are some multilingual articles for every article in Wikipedia, but there are some information discrepancy between each language's Wikipedia. So it prevents fluent communication between different language societies of the world. Also, there are so much duplicate effort to make the data for each language. So the other one is large-scale processing. We have much more data than currently existing data. And first one is ontology infrastructure technologies are still in its incubating stage. Ontology means there's some taxonomy and some semantic relations between concept and instance. So we need data fusion and ontology quality verification technology, and also gathering information from web documents. It's not yet automated. So also we have not so mature technology because it is still has a low precision problem. So in KAIST, my team has a project about web data synchronization across multiple languages. It is beyond the translation because every article in different languages has a different amount of information and different quality. So for example, in the left side picture, you can see birds are building. For example, in the English page, it is a concept under a template called hotel, but in Greek page, it is, they use the template of building. In Korean, they use skyscraper template. It's different metadata, different template, and different quality and quantity of issue. So input box is a kind of summarized information that can be extracted from the Wikipedia, but the content is different. Depending on the different culture, intentions, and perspectives. And also, inconsistency of quantity and quality issues. For example, English has more than 3 million articles, but in Korean has only 23%. For quality issue, they have some overlapping. Of course, there are so much conflict. So challenge is translation problem or standardizing the template ontology or input box ontology building, or how to build up, how to transform the category and tag cloud structure to well-formed taxonomy and so on. So in KAIST, in order to deal with these problems, we have just launched the Web Science Division that is led by my colleague, Professor Meng Sung-hyun. We think that there are three areas of the interdisciplinary study. Of course, in the red circle, we have computer science, traditional computer science curriculum. But in the left-hand side, you see web infrastructure and application curriculum for social network or security problem, web architecture, high-performance computing, and web software engineering, and also web-related social and economic courses. So, in summary, for this web science curriculum, we think that we can classify the curriculum into 5 categories. For example, web platform and principle, and web growth, evolution, knowledge acquisition and sharing, social dynamics, and safe web service and privacy. Thank you very much.
Thank you very much. Dr. Liu?
Yeah. Good afternoon. My name is Jimmy Liu. I came from Agency for Science, Technology and Research, Singapore, in short, A-STAR. Before I start the talk, I must confess that when Tony sent me an email, asked me to be a panelist, I have never read the book before. And after receiving his email, I quickly sent the email back saying, oh, yeah, I may not be qualified to comment on the book because I haven't read the book. And I will be very glad to be a good audience. Yeah, but after I sent this email back, I started to read the book. I was very much inspired by the book, some of the ideas and some of the futures, okay, this data-intensive science can provide. So I was hoping, okay, Tony will not reject me. And I'm very glad that, okay, Tony sent me an email saying, hey, you are most welcome to comment from your own research perspective, okay, even though it may not be too much close to the topic. And that's the reason why I'm sitting here to present to the audience. Yeah, the topic of my presentation is the first paradigm from medical imaging and medical image informatics perspective. Yeah, because we are a government research institute. We focus on research projects. So we have worked with hospitals for about 6 years, and I would like to share my experience and to share some of the ideas highlighted in the book, The Fourth Paradigm. I'm heading a medical imaging research group. We have about 20 over people. We focus on 2 areas of research. Computer-aided diagnosis from image and also image-guided robotic surgery. So both of these 2 projects involve a large amount of imaging data manipulation. And slowly, to dig the root of the problem, we are also studying the genome-wide association study to try to study the association of a disease and also the human genome. Because there are so many diseases, I'm going to use one simple case to showcase our work, and I will comment on the book itself. We have a project called Agalaea. Agalaea is the name of a Greek goddess of the brightness. So we are doing eye imaging research, so we hope the project can provide certain brightness, okay, to the patient. It actually stands for Architecture for Automatic Glaucoma Diagnosis and is genome-wide association study through medical image informatics. As many of you know, genome in Mandarin is called 青光眼. Yeah, it's a kind of eye disease. But this eye disease, unlike cataract and other disease, once you got a disease, it cannot be cured. So the detection of the disease is very important. And the deadly news is that according to the ophthalmology survey, 90% of the people does not know, 90% of the glaucoma patient does not know he has this disease. So the early diagnosis is very, very important. For people about 40 years old, the prevalence of the disease is about 3%. So I'm very sure now we have about 300 people, and we may have about 10 people having this disease. Yeah, and many of you, according to the statistics, yeah, maybe more than half of you do not really know you have this disease. And the disease is caused by the damage of optical nerves. And it has the symptom that you will lose the peripheral vision. So which means, okay, you may not be able to see your 2 hands here if you look straight. And the progression is very slow. And once you start to lose your vision, the optical nerve damage is already caused, so it cannot be repaired at all. So what we have developed is that from the fundus image, yeah, we will be able to see the damage of the optical nerve. And from that, we will be able to do the early diagnosis and to start the early treatment. And we are very lucky to work on a very huge database containing the different races of people from Singapore, Chinese, Malay, Indians, and Australian Caucasians. And we are also very lucky to have the genome information of those people, and we are able to study the association of the disease and the human genome. And also we are able to study the image cue changes with the particular people's genome. So having talked a lot about the project, okay, I'd like to, from the project perspective, comment a bit on the force paradigm. We are very much impressed with the concept highlighted in the book, particularly in the talking about the knowledge liquidation, data acquisition, and using a very unified model for the system integration. And we have a lot of experience in using machine learning. Many years ago, when we talked to the ophthalmologists, okay, they do not allow us to use machine learning to do diagnosis because they don't like this kind of black box approach. But after working with them for a few years, they very much appreciate our work and allow us to use machine learning approach. And the cloud for healthcare, we believe, is very useful for telemedicine. And we do have a lot of experience, okay, talking about the multidisciplinary curriculum education for healthcare related research. Okay, that's all. Thank you.
Thank you very much. And lastly, Professor Suji, but I think you'll see that Dr. Liu is doing a perfect example of fourth paradigm science.
Okay, so I'm from University of Tokyo, and also I've been engaged in the activity of National Center for Text Mining in UK, which was established by the initiative of Tony, and I'm very much sort of involved in e-science through text mining activity. So the first question posed by Tony, what are the important technologies for applications in data-intensive science? My answer is somewhat text-related techniques. So here we say TEST. T means theory, E is experimentation, S is simulation, and D is data. So that's a constitute a sort of element in fourth paradigm. And I believe the text is a useful addition to those four dimensions. First of all, scientific publications are increasing enormously in these days. So for example, about 500,000 papers are added to Medline. Medline is a text database of biomedical domains. That means almost 2,000 papers, or less than 2,000 papers, are being added to that text database every day. So enormous amount of text are being added. And also some simple protein like G protein coupled receptor, about 14,000 papers are published on these specific proteins. So the information in text are enormous. And the other problem of scientific research in these days is we have enormous computational power, which enables us to do some simulation in a large scale. And also, experimental method actually produce very huge amount of data. So we have simulation on one hand and raw data on the other hand. And we cannot really link up these two ends of the two sciences. So the keyword, which is again mentioned by Tony's talk, is semantics. So that means we need a kind of a knowledge integration through semantics by which you can interpret the data produced by the experimentation, and you can focus on certain models which are meaningful to do some simulation. Okay? So here the kind of a typical form of knowledge integration in biological research, which they call pathways. Okay? And each So in this network, each node corresponds to proteins or chemical materials. Okay? And the biologists read a large amount of, huge amount of papers to construct these pathways. Okay? So the biological facts actually scattered in published papers, and in order to understand the complexity of the whole life system, they have to put those individual facts scattered in the paper in the form of network. So they read a huge amount of paper to construct, to build coherent interpretation of biological facts, which are pathway. Okay? And not just single pathway, but hundreds or thousands of pathways are being constructed by biologists just by reading papers. Okay? So here are the sort of things which we have to do. On the topmost part is simulation, some kind of a quantitative part of the model. And then the lower part is a published papers where the facts are scattered. And in the middle, a kind of an integrated interpretation of biological facts. But these three informations are mutually related with each other. The facts are interpreted in terms of coherent system, and then that system can be simulated in a quantitative way. And also, biologists want to go the original papers in order to understand what's happening and so on. So these three elements have to be interrelated with each other. So theory and simulation is one hand, and the raw data experimentation on the other. And inside the middle, we call some kind of knowledge space. Okay? And in order to link these two extremes, we need kind of a knowledge integration of the system. So that's what we are doing. So this is a kind of a simple demonstration of our system. Here the sort of a pathway, and by just clicking the part of the pathway, you can retrieve the relevant papers from large collection of the papers. Okay? So we have very fine-grained integration of interpretation and original paper. Okay. So the next step would be not only knowledge integration, but we want to go a bit further down. Based on this integrated information, the system may be able to generate a kind of scientific hypothesis or the knowledge discovery. So which need huge collection of resources, computational power, and also the cooperation among the people. So the cloud may play a significant role in this integration of data, theory, model, and knowledge.
Thank you very much. Well, I'd now like to throw the questions to the audience, and there should be some microphones out there. Are there who would like to start the discussion? While you're thinking about it, I'd like to just quickly ask the panel, is there, the question over here, yes, okay. No? There's one coming. No?
Okay. Well, perhaps I'm pointing to the Professor Tsuji in his last slide. So you gave the picture of this theory simulation on one hand and this experiment and data on the other hand. So from one way and the other way, so what sort of the information processing technology can be applied for one way or the other way? Because you might say that the machine learning for one hand, or some other more kind of sort of AI-like technique, all AI-like a technique. I can envisage, but so collecting huge data, and we have to interpret that data from each individual scientific disciplines. So we are just providing, it seems that we are just providing huge database space and let other people, I mean, the scientific people do that the rest of the real good work or something. So sort of I'd like to know, so comment.
Okay.
I think that the linkage between the huge amount of data and the model based on that data cannot be really automatized. So the scientists are between in these two. But what's happening now is the scientists are flooded by just a big data and also big computation power. So they cannot really link up these two. So what the computer system can do is to help those scientists to locate where the relevant data are stored and what kind of the papers are actually published in that part of the data. And that paper are somewhat relevant to this simulation model. So that linkage are really missing now. So all the scientists are struggling to reconstruct those links, which have already been done by other scientists, but that part are not shared by the community as a scientist. So my guess is that the computer system can help those linkages. And through, in order to achieve that linkage, we may need some kind of machine learning or semantic processing and so on. So my intention is that the computer system to really linkage these two automatically.
Professor Choi, would you like to comment? Because you're using semantic web technologies as well as natural language processing.
So in my talk, there is a synchronization project to translate the information of an article in Wikipedia and also the synchronize the obsolete information and also update the information. So, but it is a tremendous job to translate all of the things, and every day we have to translate. But in Wikipedia, there is some pivotal input box that can be shared among several languages. But I think that input box is the pivotal semantic data that can be more ontology-like systematic things. Then first thing is to translate the content of the article to input box, such a kind of table, and then we can share among all of our languages, and then finally we can generate from input box to the text of the other languages. So it is some indirect synchronization by using the semantic technology in this large amount of web space.
Thank you. Should we take another question? Yes, over there. Thank you.
Hello, I'm Sung-Hyun Meng from KAIST Korea. Actually, I'd like to raise a question to Tony Hay. Reflecting that there are a couple of panelists working on text mining or natural language processing. And in one of the slides that you showed us, the data that you're concerned about are mostly like sensor data or experimental data or simulation. But I wonder why you didn't include the data on the web itself that's generated by human beings. And Professor Tsuji talked about data generated by scientists, but nobody seemed to care so much about the data generated by the lay people, the huge amount of web data. So I wonder whether you are excluding web data for the false paradigm, or that was a mistake, or some other reasons.
No, I can certainly give you an answer. I do think analyzing the web data is important, and you know, the Wikipedia example is one case. The reason why it was excluded because we were actually talking about scientific data and about applying computer science technologies to scientific data. And whatever the web data is, it isn't specifically about a scientific field. It has lots of implications for sociology and social networks and things like that. And that's a valid area. But so we had explicitly excluded it, but it doesn't mean to say it's not interesting. So I think I agree with you. Any other comments from the panel? No? Okay. Yeah, a question over there.
I want to ask each of the panelists, is data-intensive science mature enough to offer a course to a first-year graduate? If so, what are the two concrete principles or concepts that we need to teach?
Thank you very much. So, do you have a course in multidisciplinary data science? So, Professor Huai, do you want to make a comment to start?
Comments. So I think so for data science, maybe we face a new challenge, but the science may be equal. So for the first graduate, I think statistics and dynamics, maybe we should provide a teaching course for students for the methodology or science to analyze the data. And then another way, I think, the machine learning, also data mining, how to provide a data analysis course is also an initiative.
Thank you. There's one suggestion. Professor Choi?
I think we need some domain knowledge because of course, web data covers all of the domains, but we have some domain-specific application, but enormous of our domain. So I think we have no experience about data and the domain-specific application, but I think we need more a short course in the first year of graduate school to cover the variety of domain knowledge. For example, 1 week or 1 day course is necessary. People going to the further study.
Jimmy?
As we are a research organization, so we don't have undergraduate students. However, I would like to comment a bit about this multidisciplinary. In the past, people have been thinking about people should have multidisciplinary so that, okay, when they go to market, especially in the healthcare industry, people are talking about a lot about biomedical engineering. And from our experience dealing with medical doctors, seems okay, the people who study the biomedical engineering are not that welcomed because, okay, for a particular application, the domain expert would actually treasure your technical skills rather than your particular domain skills. So I think, okay, if you can set up a good alliance, you may, if you are engineering students, I would suggest that people focus more on the engineering, okay, rather than the application. Of course, okay, he need to know a bit, okay, but we need to have a kind of balance, okay, so that, okay, he will still need to focus on one main area and that the other area become the sub. Thank you.
Yes, Suji.
I don't have any strong opinion on that, but I don't want to teach very technical things to the undergraduate student to the first year. So what we have to teach is a sort of nearly the basic way of looking at the problem from a computer or information science point of view.
Okay, so I mean, I can give you a comment as well. I think that it will vary on different fields, but for example, at University of California, Santa Barbara, Jeff Dozier and Jim Prue talk about data management in the environmental sciences, and knowing how to manage databases, schemas, and things like that. And I think that machine learning technologies, understanding a little bit about Bayesian statistics, understanding about dealing with uncertainties are important. And those are some of the basic groundings. But I would agree with Jimmy that I think that the idea that people will employ a generalist, I think you have to have deep domain knowledge, but you also need to have some other skills as well. So I think computer scientists who have their deep computer science knowledge need to know something about the sciences, and scientists who have a deep domain knowledge in science need to know something about the sorts of technologies that could be important. So, you know, things like semantic web technologies may end up being important. So understanding, having an appreciation as to what sort of weapons are out there, what they can do, I think is something we can teach. But of course, I'm no longer in a university now, so I don't have to teach them. Yes?
I'm Li Junwang from Jiao Tong University from Taiwan. Recently, I read or listened to a story that it says the danger of the single story. So it seems that we now have collect a lot of the data and try to analyze the data and create some information. So my question is there any technology to make sure we can get a second stories of this collected data? Because I'm worried about this. If we just have the one single story, may not be able to, as a scientist, we always question, is that true?
So, sorry, you mean there's one copy of the data?
No, I just, if we have one data, that could have a different meanings. But how can we get the second, is there any technology that can make sure we can get a second different stories?
Okay. I mean, does Suji, you want to comment on that?
I think so all about scientific communication. I think it's not really just give a single interpretation to the data, but we want to make make clear how many different interpretations actually exist on the same data. So by linking the data and interpretation, reveal that a multiplicity of an interpretation exists. So that's more important than just giving single interpretation to the data. It's more, we have to show the ranges of interpretation given by scientific papers to the single paper. So that part is now missing. The data is here, and someone write a paper on that data without sharing that data. But if we can share the data, we can also share the interpretation as well. So,
other members? I could say something. I think it's very important that the data, as Professor Suji says, is available for other people to verify, so that you may have done an analysis of the data and come up with one interpretation, but other people need to be able to get access to that data and check that or combine it with their other data. So I think open data for science is very important, and having multiple people looking at it is important for science too. So I'm not sure there's any automated tool to do that. I think it's scientists themselves. We have time for a couple more questions.
I'm Xu Xiaofei from Harbin Institute of Technology. So I have another view about the data-intensive science. I think, yeah, so the people who research on data-intensive science pay more attention on how to collect the data, how to build data, and to find the information knowledge, and to offer the information and knowledge. But in fact, so we should consider, if we change the view, we should consider how to use this knowledge, this information and the data. So in such way, I think so we should pay more attention on services. Yeah, so how to, like the description by Professor Huai, yeah, so we should consider how to build the architecture of services and how to facilitate the service to support the application which is the real demand of customer. Yeah, so what's the opinion of the panelists?
So you mean about we should use this to build knowledge services, these sort of things?
Yeah, knowledge services and service for application, and how to build the application based on services related to the large mass state. Yeah, so this is my question.
So I think this is really related to the sort of scientific infrastructure question you raised. Do you want to make a comment?
So thank you. So I also have a comments about that. So the data processing, so analyzing, capture, and the curation is very important thing for analyzing of data. But in other way, so how to provide a platform for dealing with data. So I think, so how to provide the resource scheduling, allocation, so provide the power, I mean the computing power and the storage for data processing. In other way, so how to provide software developing environment or tools for different discipline user to develop their own application or service. So I understand maybe you see, oh, maybe we change our idea. We just provide the tools for the different discipline scientists or user. They can develop their own application for information knowledge, right?
Thank you.
Yeah, thank you.
Okay. Any other comments? Jimmy?
I would just like to comment that in the healthcare industry, there are two different concepts. One is called diagnosis and one is called prognosis. And for our case, we use a lot of genome association study to study huge amount of data to do diagnosis. And once the diagnosis is done, okay, we can use that knowledge, okay, to do prognosis, yeah, which can help people to predict disease and do early treatment. I fully agree with you. Okay, so the intensive data science, okay, should help application. Thank you.
Thank you very much. Any other questions? Well, I think it's almost time to go to the cruise. So what I'd like you to do is to thank our panel once